Okay, so let us just recall that if A is Noetherian, respectively Artinian, and M is finitely generated A module, then M is Noetherian. Respectively Artinian. This follows directly from the onto homomorphism A into M. A chain of submodules of M is a sequence M naught M equal to M naught contained in M1 so here each one is a strict inclusion of submodules of M and a composition series of M is a chain such that mi mod mi plus 1 is simple. What do you mean by simple? It has no non-trivial subgroups other than 0 and itself. So, there are no subgroups submodules of this module other than 0 and itself. Okay. Okay, so if let me maybe I will write this as m minus 1 mn minus mn equal to 0. I mean I am talking about composition series that terminates at 0. That means M1 is a maximal submodule of M naught, M2 is a maximal submodule of M1 and so on. Okay. And the length of this chain is said to be n. Let us look at one or two examples. So, if the module itself is a simple module, then your composition series, this is a composition series, right? ZP is a simple Z module. So, this is a composition series. Suppose I take Z4, let us say. Can you give me a composition series for Z4? Z4, Z8, Z2. See, when we talk about Z2 contained in Z4 etc. the ideal generated by 2 Z4 and 0. You should not really say that Z2 contained in Z4. Now that has a lot of scope for confusion. Okay. So this is a composition series of Z4. Another composition series of, let us say, Z12, then 6Z12, 3Z12, sorry, other way around, right? 3Z12, 6Z12, 0. What is, yeah, can you give me another composition series for Z12? Two Z12, 4 Z12, what is 8 Z12? 8 Z12 will again be 4 Z12. There are no proper submodules of 4 Z12. Right? 4 Z12 is 0, 4, 8. It does not have a proper submodule. Similarly, I have one more, right? I can say 2 Z12, 6 Z12, 0. They are all composition series. So the composition series of Z12, all of them have length 3, right? What about take the Z module Z itself? Does it have a composition series? I can start with, if I want to construct a composition series, I should find a maximal submodule. So let us say 2Z, a maximal submodule of this 4Z, a maximal submodule of this 8Z, and so on. It never terminates. So Z does not have a composition series. If a mod, okay, I will come back to that. So the first thing that one tends to think about, suppose you take a module which has a composition series, okay, and suppose it has different composition series. Is it true that all of them have same length? In this case, right, Z12 has same. So this is indeed true. Let M be a module with composition series of length n, then every composition series of M has length n. Moreover, every composition series every chain can be extended to a composition series. Okay. So, M can have many composition series. So, let us denote, let L of M denote the minimum of lengths of composition series of M. I want to say that every composition series is of this length. To start with, I know that that n is bigger than or equal to m, right. So, observe that length of m is less than or equal to n. Let n be a submodule of can we say that L of n is less than L of m? First of all, will this have a composition series at all? Will n have a composition series? How can we construct a composition series for n? Yeah, take a composition series for m and then intersect with n each of that will give me a composition series for n. So, therefore, n will have a composition series. Now, what will be the length of n? Will it be strictly less than m? I mean, will this always hold true? Okay, let us look at this. So, let m equal to m naught contained in m1 be a composition series of m. Now, I take Ni to be n intersection Mi. Now, what can we say about, see, then we have, then there is there exists a chain n naught is n because that is m naught is m, n is a submodule, therefore, m intersection n is n naught, I mean n itself. This is contained in n1 nn equal to 0. So, here see in this one we will have to put less than, I mean subset or equal to, because we do not know how, there can be two of them which when intersecting with n can give rise to only one submodule. So, we will just put like this. Now, what can you say about Ni intersection Ni mod Ni plus 1? What is this? This is Mi intersection n mod Mi plus 1 intersection n. Now this injects into mi mod mi plus 1, right. This one, if I take any x bar here, so x plus ni plus 1, if I map to x plus mi plus 1, this will be an injective A module homomorphism. So therefore this injects into mi mod mi plus 1, but then this is a simple A module. So therefore this is either equal or 0. Since mi mod mi plus 1 is simple, either ni mod ni plus 1 is equal to mi mod mi plus 1, or ni is equal to ni plus 1. So if ni is equal to ni plus 1, I just remove it. Okay. So by deleting the corresponding repeated terms, what I get is a composition series. By deleting the repeating terms, so let me call this chain 1, we get a composition series for composition series of n. Therefore length of n is less than or equal to length of m, right. Now suppose I take what is meant by, see, our aim is to show that it is strictly less, n, if n is a proper submodel, then this is strictly less. What is meant by this? These two are equal. If L of n is equal to L of m, what does that say? That says that here none of them is repeating. That means nowhere this happens, or in other words, n1, what is n minus 1? Look at what is n minus 1. This is n intersection mn minus 1. So this is not equal to, so nn minus 1 mod nn is equal to mn minus 1 mod mn, but nn is, what is nn? That is 0. Therefore nn minus 1 is mn minus 1, right. Similarly nn minus 2 is, now nn minus 1 is mn minus 1, therefore pulling back ultimately we get and that implies nn minus 2 is mn minus 2, so on, ultimately we get n is equal to m. So therefore if n is a proper submodule of m, then length of n is strictly less than length of m. See, this has a very interesting consequence. Let m equal to m naught contained in m1 be a composition series of M. Then length of M is bigger than or equal to length of M1 plus 1, right, from the previous discussion. This is bigger than or equal to length of M2 plus 2 length of Mn plus n, but Mn is 0, therefore this is n. So L of M is bigger than or equal to n. If I take any composition series, L of M is bigger than or equal to n. But L of M by definition, what is it? Minimum of lengths of composition series, which means if you take any composition series that has length L of n. Okay. Okay. Now to prove the last part, suppose I take, let mk m naught is m, m1 be a chain of submodules of M, then we know that length of mk minus 1, this is less than length of M. So when you say that, it means mk minus 1 has a composition series and it has finite length, this is a well defined. So I can find a composition series for mk minus 1. Okay. Now if mk mod mk minus 1 is not simple, that means mk is not a maximal submodule of M. Maximal submodule of mk minus 1 is not a maximal submodule of mk minus 2, and length of mk minus 2 is again finite because it is less than length of m naught, therefore it has a composition series. Take the, mk is not a maximal submodule, therefore you can extend it, keep doing this and find a composition series for. What we are doing is basically we are inserting modules whenever it is not a maximal submodule. Okay. This, the fact that length of any, if M has a composition series, then any proper submodule has a composition series and the length is less than the length of the composition series of M, makes us enable us to complete this process. Okay. So less than length of M, then mk minus 1 has a composition series if mk minus 2 mk minus 1 is not simple, then mk minus 1 is not a maximal submodule of. So, if I take not a maximal submodule of oops, mk minus 2. So, choose a maximal submodule of mk minus 2 containing mk minus 1 and I kind of apply induction, you keep doing this. So, let mk minus 2 prime be a maximal submodule of mk minus 2 containing mk minus 1 and keep doing this. So, therefore, this length has proceeding like this. So, what we have seen is that if a module has a composition series, then every composition series is of same length. Okay. So, therefore, if M has a composition series, then there is a unique integer associated with M, which is the length of the composition series, that is unique. The length of the composition series of M is called the length of M. Okay. And if M does not have a composition series, then we say length of M to be infinity. Okay. So, we have already seen examples where it is finite length. So, what is length of Z12? 3, length of ZP 1, length of Z4 2. Okay. Suppose I take M to be, take a ring A and look at a maximal ideal M power n. Okay. I look at M is a maximal ideal in A and look at the module M equal to A mod M power n. Okay. Now, can you give me a composition series for this? I want a submodule of M. M, yeah, which is same as M, right? M mod M power n contained in, containing M square mod m power n what is A mod m power n modulo m mod m power n? Is this a composition series? See, how do I say this is a composition series? If this is, I call this M1, M mod M1, is this simple? What is M mod M1? M mod M1 is, this is isomorphic to A mod M, right? That is a field. Therefore, this is simple. What about M mod M square, M mod M power n modulo M square mod M power n? What is this isomorphic to? M mod M square. This need not necessarily be isomorphic to A mod M, or this is M mod M square is an A mod M module. It is an A module, at the same time it is an A mod M module, but A mod M is a field. So, this is a vector space over A mod M, right. This could be a finite dimensional vector space. This need not be a of dimension 1 like this. So, there could be many, no, this need not be simple. If this is an n dimensional vector space, then suppose this is generated by x1 bar up to xm bar, then I can, within this I can have this x1 bar up to xm bar, x1 x2 bar up to xm bar, xm bar, right, to 0. This itself is a composition series of M mod M square, right. So, therefore, this need not necessarily be a composition series. I can insert in between and get a composition series. But then each time what we are going to do is insert finitely many, well, assuming that M is finitely generated. If M is finitely generated, each time I will have finite number of modules in between, and this will be a module with composition series with finite length. Okay. So, this implies that if M is a finitely generated A module, finitely generated ideal, more generally if I assume A is Noetherian, okay, then length of A mod M power n is finite. A mod M power n has a composition series. That composition series need not be what I wrote there, that now A mod M power n containing M mod M power n containing M square mod M power n and so on. That need not be a composition series, but we can insert in between, there could be many, but we can insert and ultimately get a finite composition series. So, this is another important property of composition series, modules with composition series. M has a composition series if and only if M satisfies AC's ascending chain condition and descending chain condition both. If a composition series M has a composition series, then it should satisfy ascending chain condition and descending chain condition. So, I mean one way is immediate. If M has a composition series, any chain can be extended to a composition series, that is what the previous result says, which means any chain has to be finite, whether it is ascending or descending, whatever wherever you start with, it has to be, it has to terminate, right. So, therefore, this if M has a composition series, then any chain of submodules of M has finite length. Therefore, M satisfies ACC and DCC. Any chain will have only finitely many elements. So, ascending chain condition and descending chain condition both are satisfied. Now, suppose I conversely let M be M satisfy ascending chain condition and descending chain condition. Okay. I want to say that it has a composition series. So, we construct a composition series. Okay. Now, let M1 be a maximal submodule of M. I can say this because M satisfies ascending chain condition. What is meant by ascending chain condition? It is any increasing chain terminates, equivalently any collection of submodules of M has a maximal element, right, and equivalently every submodule is finitely generated. These are three equivalent conditions. Now, I know that M satisfies ascending chain condition. Therefore, I can choose a maximal submodule of M. Okay. Now, I look at, so therefore, now I look at M1. I look at the collection of all submodules of M1, which are anyway submodules of M. Submodules of M1, again because of M satisfying ascending chain condition, this will have a maximal element. Okay. M2 be a okay. So, we can, since M has ascending chain condition, M1 such an M1 exists. Okay. Then now sigma 1 be the collection of submodules of M1. This is a collection of proper submodules of M1. Let M2 be a, in fact I should have chosen M1 like this. Let sigma be the collection of all proper submodules of M. Let M1 be a maximal element. Now let M2 be a maximal element in sigma 1. Then I have, so continuing like this, I get a chain of submodules we get M contained in M1, contained in M2 and so on. Since M satisfies descending chain condition, there exists K such that Mk is 0, because if it is non-zero, I can, if it has a non-zero proper submodule, maximal submodule, I still can go further down. So therefore the chain terminates. M has a composition series. So having composition series is equivalent to saying that it has both ascending chain condition and descending chain condition. Okay. So this is like, length is pretty much similar to the dimension of a vector space. It's ring theoretically very close. If I have a submodule, if I have a subspace W of V, if it is a proper subspace, then dimension of V is strictly bigger than dimension of W. Moreover, we know this dimension of V is equal to, this is rank nullity theorem, you can say dimension of W plus dimension of V mod W, right. I mean, how does this come? So if I look at I have this exact sequence. What rank nullity theorem says is that dimension is additive on the short exact sequence. Dimension of W minus dimension of V plus dimension of this is 0. Okay. So is this true for the case of modules? So suppose I have a M prime to M to M double prime to 0, modules of all of them have modules of all of them are modules of finite length. Now suppose I have a, see, I want to say that is it true that length of length of M is equal to length of M prime plus length of M double prime. I only have to produce one composition series of which satisfy this property, composition series of M with length equal to this plus this. Can you think of one? So here you can think of M prime as a submodule of M and M double prime as M mod M prime, right. So you can think of this M prime as a submodule of M and M double prime equal to M mod M prime. M mod M prime has a composition series. So, let us look at M double prime. See, this will be, this has a composition series. Any submodule of this is of the form some submodule of M mod containing M prime modulo M prime. If I have a submodule K of this, then K I can think of this as some N mod M prime, where N is a submodule of M containing M prime, right. So, I can write like this, M prime, which is M mod M prime contained in M1 mod M prime Mr minus 1 mod M prime and 0. What is 0? This is M prime mod M prime, right. This is a composition series of M double prime. Now, suppose I have a composition series of M prime contained in M1 prime Ms. So, this is Ms minus 1 prime contained in Ms prime, which is 0. Now, can you tell me a composition series for M? This composition series of M double prime, this is composition series of M prime. M, right, M1 contained in Mr minus 1 Mr, which is same as M prime contained in M1 prime Ms minus 1 prime Ms prime equal to 0. Now, look at each quotient. M mod M1 is same as this modulo this, but this is a composition series. Therefore, this modulo this is simple, this modulo this is M mod M1, therefore, this is simple. Similarly, at each stage the corresponding quotient is same as the corresponding quotient here. Therefore, each time it is simple. Therefore, this is a so length is additive on short exact sequences.